Right, so welcome back. So today is Thursday, April 12th, and we just released the new module, the Test for Proportions module. It's week 12. So I just wanted to check if you had any questions before we started. Meryl, do you have any questions that you want to go over? Happy to go over anything that you've been confused about, or we can go over the new material if you'd prefer. Okay, so now that we've gone over the test for means lecture last week in the last module, this module will cover test for proportions. And as you can see, we're coming up to the end of the semester. We just have 2 more modules to learn, and then you will have learned all the material for this semester, and we'll have a course review. So just to touch on the overview of this lecture, we'll talk about the sampling distribution of a proportion, one sample z-test for a proportion, inferences for the difference of 2 proportions, and inferences for the difference of 2 means. So this is similar of a lecture to what we had last week with dealing with the test for means, except now we're just dealing with the proportions. So when we talk about population parameters for this lecture, we recall that the mean of the population is referred to as mu, while the mean of the sample is x bar. For proportions, we will usually refer to the population parameter as p hat with the caret over the p to represent the proportion in the population, while the sample the sample parameter will be p for a proportion. And sometimes you'll see pi. So that's just the Greek letter to substitute for p. So just mindful of that. And a proportion can be thought of as a mean. So we are dealing with binary events, and we can code an approval as 1 and a disapproval as 0, or it can be a success and a failure. And then from that sample, we can calculate a proportion as a mean. So in this example, we have 4 observations, and 3 of them had approvals coded as 1, and 1 person had a disapproval coded as 0. So if we take an average of those 4, we come up with a p hat is equal to 0.75. So that would be what our p hat population parameter would be, so long as the success failure condition holds and applies. And to talk about what the success failure condition is we assume that we calculate p hat from a random sampling distribution of p hat is approximately normal, so long as we can see at least 10 successes and 10 failures. So that is to say, your sample size n times your p is greater than 10, and your sample size times your complement of p, your failure rate, will be greater than 10. So although we don't know the population proportion p, we can use the sample proportion p hat to test these conditions. We calculated p hat to be 0.75, and if we look at the success failure condition, we multiply out the successes, the expected successes, and the expected failures. We see there's 3 successes and 1 failure. Both are less than 1, or sorry, both are less than 10. Thus, we would not necessarily expect the sampling distribution of p hat to be normally distributed. So in this example, we're looking at a census data from Turin, Italy, and we have a categorical variable, one that's coded binary as yes or no. What we can do is represent a yes equal to 1 and no equal to 0. And we can find a proportion of that numerical variable p, which we see here is about 0.33, so about 1/3 of the people. So now we can test for the success failure condition with a sample size of 3. With a sample size of 3, they're both going to be less than 10, because 3 is less than 10, first of all. So we know that the success failure condition would not hold here. Therefore, it's likely to fail with a small sample size. However, with a larger sample size of 30, that actually would hold. So that's basically the cutoff point, because 1/3 of 30 is 10. So you would need at least a sample size of 30 in order to satisfy the success failure condition here, which is to say that you expect there to be at least 10 successes and at least 10 failures. So for a sample size of 50, that would hold. So now that you've satisfied your success failure condition, you can actually model a normal distribution model for the population, for the sample parameter. So you can actually use the sample parameter to model the population parameter using a normal distribution model. So here's an example of that using, we can see as we're increasing the sample size, the normal distribution model is becoming more and more normal. So because p hat can be understood as a sample mean, based on a variable with values of 1 and 0 only. As long as the success-failure condition holds, we can then model it using the standard normal distribution. And we could also use our one sample z intervals like we had in the previous week. So we know that the distribution will be centered on the p-hat, but how do we calculate the standard error? So the standard error for the purposes of dealing with proportions will be the sample size. So, in the previous example, we were using sample size divided by the square root of n. But since we're only dealing with values of 1 and 0, we can also write out the standard error here. So we can use our standard deviation is equal to the square root of the success proportion multiplied by the failure proportion. So here we have a success proportion of 0.33 and a failure rate of 0.67. If we multiply those two together and take the square root, we get 0.47. And that will be divided by the sample size to calculate the standard error. So just to reiterate, the standard error for this distribution will be the square root of p times 1 minus p over n. And it will be centered at key. And then once you have that standard normal distribution, you'll have a distribution centered at 0 with a standard error of 1. So without additional information, the single best guess for the population proportion p is going to be the sample proportion p-hat. And you can use a z interval, the confidence interval, using this formula, p-hat plus minus z alpha over 2 times your standard error, which we just discussed how to calculate your standard error. So now we can look at a given example with the health insurance data set, the ACS data set. And our question is, what proportion of Americans lack health insurance? So we have 343 respondents in our sample. And to calculate the z interval, we're going to use the point estimate of 0.12 to be the proportion of Americans without health insurance. And we know the sample size is 343, so we can find the standard error from our formula. We just plug in the numbers and we find that the standard error is equal to 0.0175. And now we can use an alpha of 0.05 and thus a z critical value of 1.96 to find that our confidence interval will be 0.12 plus minus 1.96 times 0.0175, which will give us a confidence interval from a lower range of 0.0857 and a higher range of 0.1543. So we can say that our confidence interval, we are 95% confident that the true population proportion of uninsured people in the United States is between 8.6% and 15.4%. So this will give us an estimate of what the true population proportion is for uninsured people in the United States. Accordingly, we could also use one sample z-test as well. Like we did in the previous lecture, we were dealing with hypothesis tests for the test of means. This will be a similar process, except that we will now be dealing with proportion of people. Now we'll be dealing with proportions. So an example of this is we can look at the proportion of people voting for a politician, we're curious if it's greater than 0.5, 50%, or we can look at the proportion of people who support marijuana legislation, and we're wondering if it's less than 60%. So in order to do this, it's going to be the same steps to calculate, to find our hypothesis test as we had in the previous example. So the steps are to first state the hypothesis in terms of the null hypothesis and the alternate hypothesis. Second, we'll choose a significance level, typically 0.05. Third, we'll compute our test statistic. So we find our test statistic as z is equal to p hat minus p naught divided by the standard error, which will be your z test statistic. And we'll compare it with the critical value to come up with a conclusion. So we can either compare the test statistic and critical value, or we can compute a p-value. And then we'll make a conclusion. So what's highly recommended is also, in addition, to calculate a confidence interval as well, not only to run a hypothesis test, but also to run a confidence interval as well, just to have that additional format. So here we're looking at, we want to test a hypothesis that the proportion of Americans who think Wall Street executives are greedy is evenly split. So our null hypothesis will be that the P is equal to 0.5, and we're going to test whether that it holds true. So here we found that in our sample of 810 adults, that 83%, 0.83, believe that Wall Street executives are greedy. So now we're going to first check if the success failure condition holds, which it does, since we can see here they're both expected to have successes and failures greater than 10. So we will state our hypotheses, that being p is equal to 0.5, p is not equal to 0.5. Second, what we'll do is we'll set a alpha value and find our critical values. In this case, we're using a 0.05 alpha value, so our z critical value that we'll be using is 1.96. Next, we'll calculate the test statistics. So since we said that our p hat is 0.83 and our p naught is 0.5, and we have 810 people in our sample, what we'll do is we'll just simply take 0.83, subtract out 0.5, and then in the denominator, that will be our standard error, which will be 0.5 times 0.5 in the numerator, 810 in the denominator, and then we'll take the square root of that, which is 0.0176. So taking that standard error calculation and putting it back into our z test statistic formula, we find that our z test statistic is equal to 18.75. And that's a very, very large test statistic. So for sure, it's definitely going to be significant. So we're going to reject our null hypothesis, since 18.25 is much larger than 1.96. So we will reject our null hypothesis, and we'll conclude with the alternate hypothesis that the true population proportion is not equal to 0.5. So we're going to reject our null hypothesis in this example. And we'll make our conclusion. Finally, we can calculate a confidence interval, and we've already calculated the standard error. We already know what our z critical value is here. So it's a straightforward calculation to plug in. And we find that our 95% confidence interval is 79.6% to 86.4%. Here's another example to test whether people believe economics is scientific or not. We're dealing with a large sample size of 1,756 people. We find that the proportion who think that physics is scientific is 0.96, and the proportion who think economics is scientific is 0.54. So we want to know whether the two proportions are the same. So it satisfies the success failure condition, and we will be running a left-sided test to find out whether the proportion of people who think that economics is less scientific is less than physics, where the p-naught is equal to 0.96. We'll use an alpha value of 0.05, and since this is a one-sided left-handed test, we'll be using a z-critical value of negative 1.645. The z-test statistic for the proportion will be p hat minus p naught over the standard error, where p hat is equal to 0.54, p naught is equal to 0.96, and we know that our sample size is 1,756. So we find that the standard error will be 0.005, and that our z-test statistic will be equal to negative 84. So since negative 84 is much smaller than negative 1.645, it's a very significant value again, and we will reject our null hypothesis and conclude with the alternate hypothesis here. So we reject the null hypothesis that the proportion is equal to 96%, so that we conclude that the proportion of Americans who think that economics is scientific is not 96%, and it's less than that. So in other words, we conclude that Americans do not think economics is as scientific as physics is. And again, we can create a confidence interval here just by plugging it in, and we find that the confidence interval here will be between 51.7 and 56.3%. Again, we can look at accounting versus economics. There's 34% of people think accounting is scientific, whereas 54% believe economics is scientific. We find that the success failure condition holds, and we're going to run a one-sided right-handed test. We find that our z-test statistic in this case is 18. So again, we're going to reject our null hypothesis and conclude that more people think that economics is more scientific than accounting. And we can calculate a critical confidence interval for this as well. So that's how we perform confidence interval in a z-test for proportions. In this next part, we will deal with the difference of two proportions. And since it's a difference, we can still use a one sample z-test. So in order to compare the two, we can take the two proportions and subtract one from the other. So the point estimate will be the difference of those two proportions, which will be our best guess. And we want to make sure that it holds the success failure condition. That being said, that we have greater than 5 for each of the two proportions. And for a z-interval, we will use the proportion of 1 minus proportion 2 plus minus the z-critical value times the standard error. Where the standard error is equal to the square root of P1 minus, P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2, and we take the square root of that entire equation. again, we can use a hypothesis test for the difference of the two proportions. Our null will be that there is no difference, that this difference is 0, and our alternate will be that there's a non-zero difference here. We will choose a significance value, compute a statistic, and compare it with the critical value, and come up with our conclusion. So in this example, we're asking, do the proportion of men and women differ in the perception of Wall Street executives as being dishonest? So in this case, we're going to break it down by gender of the respondents, so male and female respondents, and we will look at those who believe that those males who believe that Wall Street executives are dishonest, which is 73%, and those, I'm sorry, females who believe that Wall Street executives are dishonest, which is 73%, and males who view Wall Street executives as dishonest as 60%. So our best estimate for the difference will be 73 minus 60% is equal to 13%, which suggests that a greater proportion of women believe that Wall Street executives are dishonest compared to men. So we'll check our success failure condition to make sure that we have at least 5 successes and 5 failures, which we do. And then we will conduct our z-test. So we will state our hypotheses that the null will be that there is no difference. P1 minus P2 is equal to 0. And the alternate will be that there is a difference, that we have a non-zero difference here. So we'll compute a test statistic. And as we can see here, we have our sample sizes and we have our proportions. So we can compute the test statistic by plugging in the relevant information into our standard error formula to find that our standard error is equal to 0.033. And we can find our z-test statistic by taking our difference of the two proportions and dividing that by the standard error to get 3.94. So this tells us 3.94 that it's a significant value, right? So we're going to reject the null hypothesis that there is no difference between the proportions of men and women and conclude that there is a difference between the two proportions. And you could calculate a confidence interval as well. So here we can plug it in. We find that the confidence interval is between, the difference of the two proportions is between 6.5% to 19.5%, which is actually a pretty sizable spread. And the whole idea is, since 0 is not contained in that hypothesis interval, in the previous example, we will reject the null hypothesis, conclude that there is a difference. So finally, we can take inferences for the difference of two means as well. So not only can we take the difference of proportions, but we could also run a test by taking the difference of two means. So in this case, we're looking at educational attainment in years, in people who grew up in a wealthy household and people and those who did not. So we're looking at inferences of mu1 minus mu2. So we're going to substitute that with the sample means of x bar 1 minus x bar 2. And our next goal will be to construct a confidence interval for the difference of the two means. And we will use the t distribution as opposed to the z distribution because it works with both small and large sample sizes. So it's a better distribution to be working with because it can handle any sample size that we throw at it. So in this case, we're dealing with the t interval for the difference of two means, and we first find a confidence interval by taking the sample mean of 1, subtracting the sample mean of 2, using the t critical value, and we're multiplying it by the standard error, where the standard error is equal to the square root of the variance of sample 1 divided by the sample size of 1 plus the variance of sample 2 divided by the sample size of 2. So we can use statistical software to calculate this because the t critical value will change, and it will change based on your degrees of freedom. So we can use R in order to calculate this and to run a hypothesis test. So to state our hypotheses, we'll be looking at our null hypothesis, which says there is no difference between the two means. The alternate says there is a difference. We'll choose a significance level alpha and compute the test statistic. In this case, the test statistic t will be equal to the mean of sample 1 minus the mean of sample 2 minus 0 divided by your standard error, where we said the standard error is equal to this. Then we'll compare the test statistic with our critical value, and we can find a p-value, compare that versus an alpha value, and make a conclusion based on that. We can also calculate a confidence interval, where this will be your confidence interval formula. So we'll be looking at some mice here, and we're looking at whether light exposure leads to weight gain in mice. So we find that those in the light dark cycle gained an average of about 5.89 grams, while those in the bright light on at night gained about 10.89 grams. And the sample sizes of each is 9, and the standard deviations are 1.69 and 2.52 respectively. So our null hypothesis will be that the two mice groups have the same weight gain, so that the difference will be equal to 0, and the alternate would be that they do not equal to 0. So we're using this data set here. We're running the two sample independent t-test with an R. And as we see here, we find that the p-value here is 0.0000, there's 3 zeros, 0.0002. And our confidence interval, a 95% confidence interval, is between 2.82 and 7.17. So here it's a significant result. We reject the null hypothesis and conclude that the true difference in means is not equal to 0. It's actually, the true difference will be between 2.82 and 7.17 grams. And our test statistic was 4.94 with about 14 degrees of freedom. So we can see that using this t-distribution plot, we can see that we will reject the null hypothesis because our t of 4.94 is greater than our critical value of 2.15. So we reject the null hypothesis. And again, we can look at the p-value of 0.0002, which is less than the alpha value of 0.05, which is the same conclusion that we'll reject the null hypothesis. So our conclusion is that those mice who were exposed to more light during night had an increase in weight relative to those who had a conventional light-dark exposure. So that's our conclusion, and just be careful because you don't automatically want to conclude that studies done in mice have the same effect of studies in humans. We use mice as a model organism to do testing. A lot of preclinical therapeutic testing is done in mice to make sure that the therapeutic is safe and effective. But mice have different biology than humans do, so not everything that works in a mouse will work in a human. Another example is looking at Coca-Cola and calcium levels. So we have 16 healthy women aged between the ages of 18 and 40, randomly assigned to drink 24 ounces of either Diet Coke or water their urine was collected for 3 hours after ingestion, and calcium excretion was measured. Researchers were investigating whether Diet Coke leaches calcium out of the system, which would increase the amount of calcium in the urine. So our treatment group will be Diet Coke, and our placebo or control group will be water. And here we have our calcium levels. So our null hypothesis will be that there is no change, and alternate will be that there is a change, and there's a difference. Here we find that the p-value is equal to 0.0074, which is less than 0.05. So it's a significant finding. We reject the null hypothesis and conclude that there is a difference in calcium excretion in the Diet Coke group, which we can say there's a correlation between drinking Diet Coke and excreting calcium in urine. Another example is an immune tea. We have 11 healthy non-tea drinking individuals who has to drink 5 or 6 cups of tea a day, while 10 healthy non-tea and non-coffee drinkers were asked to drink the same amount of coffee, which has caffeine but not L-theanine. So tea actually has L-theanine, which is a molecule which actually is calming. So if you ever felt calm after drinking tea, it's usually due to the presence of this molecule called L-theanine within the tea. So after 2 weeks, researchers measured the strength of people's immune systems. So that's what they're showing here. They're looking at the V gamma 2V delta 2 T cells in vitro and in vivo for memory and non-memory antibacterial cytokine responses. So this is looking at the delta gamma T cells within humans, which are responsible for immune response. So they're looking at whether drinking tea will have an effect on the immune system. And this is a study performed at Brigham Women's Hospital in Boston. So the null hypothesis will be that there's no difference in interferon gamma production between the two patients, the two groups' immune system, and the alternate will be that there is a difference. And we can look here, sample size 21, and our results of our 2-sample independent t-test is that the p-value is equal to 0.052. So it's a little bit higher than 0.05, thus we fail to reject the null hypothesis of there being no difference and conclude that there is no difference between those who were drinking tea and those who were drinking coffee in this example amongst their immune system. So even though our p-value was really close to 0.05, it was 0.052, it was just on the edge of significance, it still does not count. It's either significant or it's not significant. So in this case, because it was very close to 0.05, it was almost significant, but in this case it wasn't. So we cannot reject the null hypothesis. So that's the conclusion of this lecture. If you have any questions, I'm happy to take any questions about this lecture or anything in the class, or if you have any questions about the final project. Great. So it seems like no one has any questions. So good luck this week with this new material, and let us know if you do have any questions. Have a great night.